Okay, let's unpack this. We're about to dive deep into a stack of sources you've shared, centered around, well, a really fascinating topic.
Definitely fascinating. And maybe a bit humbling, too.
Yeah, exactly.
Hmm.
How smart is AI really when it comes to fundamental science, specifically physics?
Mhm.
You've given us this key paper on a benchmark called PhySense, plus notes and commentary, and it paints a pretty stark picture.
It really does. It contrasts those big claims about artificial general intelligence
Sci-fi and stuff, yeah.
with the nitty-gritty reality of AI trying to basically pass Physics 101.
And what's interesting right off the bat is how this paper seems to cut through a lot of the recent hype we've all been hearing.
Oh, absolutely. For the last couple of years, it felt like AGI was, just
So,
around the corner.
fueled by these models generating impressive text code.
Right. But this PhySense benchmark, it's probing something much more, well, fundamental.
Absolutely. And so our mission in this deep dive is to pull out the key insights. What is this PhySense thing? Why do current AI models struggle so much with basic physics problems? What are the implications, for research, for business, and where do we go from here?
Yeah. Get ready for some surprises, I think.
And a clear look at what humans still do uniquely well in science.
The material sets the scene nicely, contrasting what one source calls that giant upward curving arrow labeled AGI.
You see that in all the keynotes.
Exactly. Contrasting that with the reality shown by this benchmark, problems that, as one comment put it, still give nightmares to undergrads.
Yeah. Feels like a necessary splash of cold water, doesn't it? After all the breathless anticipation.
Mm.
The paper describes PhySense as not another trivia quiz. Its goal is specific. Check if a model actually thinks like a physicist.
And by thinks like a physicist, they mean principle-first reasoning. That's the key.
Principle first.
Yeah. They designed 380 problems.
Hmm.
Most are solvable in just a few lines if you have a solid grasp of Physics 101.
So not heavy calculus or complex simulations.
Nope. You need to spot a symmetry, maybe invoke a conservation law, do a quick dimensional check. It's about finding the elegant path, the shortcut.
Okay, so they took these problems, these tests of elegant thinking, and ran leading AI models against them. Models tuned for reasoning, some well-known chatbots.
Right.
And the results, well, they weren't exactly stellar, were they?
Far from it. The best performer, Gemini 2.5 Pro, barely cleared 45% accuracy,
Ouch.
and DeepSeek R1, a dismal 9%. If this were a university class, yeah, they'd definitely be looking at a retake.
Wow. And it's not just the low scores. The paper also meticulously logs the computational effort, right? Mirrored in tokens.
Yes, exactly. A human might use, say, 100 tokens of reasoning per problem.
Okay.
The machines, an average of 10,000.
10,000 tokens versus 100. That's
Yeah.
huge.
That kind of difference points to a fundamentally different way of tackling the problem. It's not just getting it wrong, it's the process itself.
And this is where the benchmark gets really insightful, I think. PhySense isn't just about the problems, but how it tests understanding.
Right. It's designed to surgically probe if the AI truly gets the principles or if it's just, mimicking patterns from its training data.
So how does it do that?
The paper describes evaluating models in 3 specific modes. First, standard zero-shot prompting. Just give it the problem cold, pop quiz style.
Okay, that shows its baseline understanding.
Then there's hint prompting. The model gets a conceptual nudge, like think about symmetry here, or consider energy conservation.
So not giving the answer away, but checking if it knows what principle to apply when pointed in the right direction.
Exactly. But maybe the most revealing mode was the no computation prompting.
No computation.
Right. The model is explicitly told not to perform sprawling calculations. The test is, can it recognize that a problem simplifies or even dissolves just by applying a basic law or property before starting the math?
That is such a clever way to test for intuition, grading its ability to spot the elegant shortcut. Can it see Gauss's law makes a calculation trivial, or does it just default to brute force integration because that's all it knows?
Precisely. PhySense, in this mode, grades the quality and efficiency of the reasoning path, not just the final number.
And this really highlights that core difference the paper stresses. Principle first versus brute force.
Yes. Real scientists, even good students, rely heavily on these mental shortcuts, conservation laws, symmetries, invariants. You see a scenario, connect it to a principle.
And often the math becomes almost secondary, or at least much simpler, like seeing an inclined plane and immediately thinking conservation of energy or force component.
Exactly. PhySense rewards that habit. Find the right conceptual pin or reflection plane, maybe know there's theorem implicitly, and the problem structure clarifies.
Conversely, the large language models tested seem stuck in that brute force mode.
They give a great example: a spherically symmetric charge distribution. A human physicist instantly sees the symmetry, knows the field must point radially outward. Simple. A typical LLM. It starts trying to integrate Coulomb's law over multiple dimensions, completely missing the elegant solution from Gauss's law.
Yeah, the paper calls this a central failure mode. They don't output elegant arguments, they generate paragraphs, pages of calculations, often wrong.
They drown in their own verbosity, as the authors put it.
And that token counter in PhySense isn't just a metric, they call it a public shaming device for this bloat.
Huh. Another example they give is a uniformly charged square plate. Where are the points where the x and y components of the electric field are equal?
Okay.
A student with decent geometrical intuition just eyeballs the symmetry. It has to be along the xy diagonal line, right?
Obvious when you think about it that way.
But the models, like Gemini 2.5, instead of seeing that simple symmetry, they launch into double integrals, get tangled in algebra, produce wrong answers.
The paper calls it LLM scientific reasoning failure.
Which connects to one of your notes. It's like they forget freshman geometry trying to impress with advanced calculus they can only mimic.
Focusing on the complex tools they can sort of manipulate instead of the basic insights they lack.
And that verbosity isn't just academic, it's expensive. All those thousands of extra tokens mean more compute time. Real money.
10,000 tokens per problem. That Claude bill adds up fast. You could fund a small science project with that.
And crucially, the paper highlights that this verbosity doesn't even buy accuracy. There's practically no correlation reported between token count and score on PhySense.
Really? None?
Almost none. Which directly challenges that common idea that you can just scale up models indefinitely to get better reasoning.
So a hard lesson here seems clear. If a model hasn't internalized fundamentals like symmetry or conservation, just throwing more compute and data at it
isn't going to magically teach it to pass Physics 101, not in this elegant principle-first way.
Benchmarks, as the paper argues, can be crucial culture shocks for a field.
Yeah, they shape what researchers prioritize. Think ImageNet for computer vision or GLUE for language understanding.
They change the game.
PhySense could potentially do this for physics AI. By making principle-first reasoning measurable, quantifiable, it moves from a philosophical critique to something you can actually build towards and test.
So if your cutting-edge physics LLM can't improve its accuracy while drastically cutting its token count on this benchmark,
you probably haven't made real progress towards truly intelligent physics assistants. You're still stuck in brute force.
what's the fundamental reason they struggle so much, according to the sources?
It ties back to their core training, predicting the next word in a sequence.
Right, that optimizes for plausible output, statistical patterns in text.
But not for logical compression, finding the minimal elegant argument, or applying universal principles. The training loss function doesn't penalize verbosity or reward finding the underlying law.
And that explains the common LLM issues: confident but wrong answers, vague derivations, wandering text.
Exactly. Even fine-tuning on massive physics datasets isn't enough, because memorizing discussion patterns doesn't instill genuine conceptual understanding or intuition.
So how do we move past this bottleneck? The paper and notes suggest it's more than just bigger models or more data.
Definitely. It likely needs changes to the architecture and training methods themselves. Some research mentioned explores hybrid approaches.
Like pairing neural nets with symbolic math engines.
Yeah, so the AI can delegate complex calculations and focus on the conceptual strategy.
Interesting. What else?
Others are looking at injecting inductive biases, building structures into the model that inherently understand physics concepts like symmetry.
Sometimes called equivariant layers.
That's right. Or understanding the graph structures common in physical systems.
And another promising direction mentioned is constraint regularization during training.
Meaning, if a model's proposed solution violates a fundamental law conservation of energy, dimensional homogeneity, it gets a big penalty during training.
Teaching the model that breaking physics rules is expensive, which is the opposite of just rewarding plausible-sounding text.
Exactly. It paints a picture of a totally new roadmap for teaching AI physics, beyond just feeding it more textbooks.
It's like redesigning the curriculum for machines, creating datasets where solutions explicitly highlight the elegant shortcuts, the principles.
Not just the final number, making the reasoning path itself a form of labeled data.
And shifting the fine-tuning goal from generating stylish prose to rewarding models for compressing their chain of thought, aiming for brevity and accuracy.
And actively learning from errors. When an AI messes up, that mistake becomes valuable data, a new test case, using failures as a study guide.
That makes sense.
The paper also proposes new evaluation metrics beyond just raw accuracy to reflect this focus on elegance and efficiency.
Like what?
For instance, measuring accuracy per 1,000 tokens, a token normalized score.
Oh, that's a really smart metric. It directly quantifies the verbosity problem we talked about.
Right. A slightly less accurate model using way fewer tokens might actually be more valuable, practically more efficient, cheaper to run.
Yeah, that one.
And testing for cross-domain transfer. If you train a model heavily on electrostatics, can it recognize and apply symmetry in, say, magnetohydrodynamics?
Can it generalize the principle, not just the specific problem type?
Exactly. And finally, integrating human judgment. Getting actual physicists to evaluate not just the answer, but the elegance, the clarity of the AI's reasoning.
Does it sound like a physicist explaining the why, or just spitting out calculations mechanically? Elegance should count.
These kinds of metrics shift the focus beyond just leaderboards. They state that compression, clarity, generalization, these are the valuable traits for physics AI.
The implications even touch on education, don't they? With students using chatbots for homework.
Yeah, there's that fear it could erode their intuition. But the paper suggests maybe the opposite.
How so?
Precisely because the AI struggles with these principle-first problems, it can be used as a powerful Socratic foil.
Ah, interesting. So you ask students to critique the AI's clumsy brute force attempt.
Exactly. Figure out where it went wrong, explain the correct, elegant solution themselves. It could actually build deeper thinking skills.
Using AI failure as a teaching tool for human understanding.
Clever. And for business, especially startups in computational discovery or VCs evaluating them, these PhySense numbers are a crucial dose of reality.
Right. If your product relies on a generic LLM for core science,
You need to be upfront about these limits and show how you're overcoming them. Specialized backends, human experts in the loop, using benchmarks like this.
using PhySense during technical due diligence could help separate real progress from, well, AGI marketing hype.
If a founder claims near-human scientific reasoning, they should be able to back it up with a decent score here, within a reasonable computational budget.
You know, reading about PhySense and the results,
Oh.
it feels oddly optimistic, as one of your notes suggested.
How so?
Well, the stark gap isn't just about AI's current failure. It's
Yeah.
a powerful reminder of what humans excel at right now,
Compressing centuries of knowledge into these elegant mental shortcuts.
and wielding them with remarkable efficiency. These shortcuts are the unsung heroes of science, maybe.
PhySense helps quantify and highlight them. If future AI closes this gap, it won't be just by memorizing more data. It'll be because they've somehow learned to appreciate and use elegance principles.
So what does all this mean for you, listening? This deep dive into PhySense and the challenges AI faces with principle-first physics. It gives us a lot to think about. It makes that distinction crystal clear, mimicking text patterns versus truly understanding the underlying rules and the elegance of physical reality.
And the sources make it pretty apparent that just scaling models endlessly isn't the magic bullet for physics intuition.
No silver bullet there.
Building truly capable physics AI systems that can actually assist discovery needs a fundamental shift, focusing on principles, structure, efficient reasoning, not just brute force and verbosity.
Yeah, this isn't really a story about AI hitting a wall. It's more a clear-eyed look at its current limits and an invitation to think about how to build something better.
Focusing on what really matters in scientific thinking,
Yeah.
that elegant principle-first approach. So for you, maybe the provocative thought to mull over is this. Given that even advanced AI struggles so much with what a first-year physics student finds intuitive, what does that tell us about the nature of understanding itself? And how much of our own human expertise relies on those elegant conceptual shortcuts we often just take for granted?
That's a great question. The chalk, for now, seems to remain firmly in human hands when it comes to true scientific elegance.
But the journey to teach AI that same appreciation, well, work like PhySense has definitely shed some light on the path forward.